This is the story of continuous simulation hydrologic modeling, what it is and how we got to where we are today. I'm Doug Bayerlein with Clear Creek Solutions. Let's start with a definition of continuous simulation hydrologic modeling. Continuous simulation hydrologic modeling is modeling the entire hydrologic cycle for multiple years, rather than planning or designing based on a single hypothetical event. For example, a 100-year storm. Continuous simulation hydrology allows us to use the statistics from a wide range of runoff or flood events to evaluate, plan, and design for hydrologic and stormwater conditions. Modeling the entire hydrologic cycle involves tracking the movement of water through all of its many pathways from precipitation to runoff and evapotranspiration. That is not something you can easily do with a slide rule or a spreadsheet. The story of continuous simulation hydrology starts at Stanford University in Palo Alto, California in the early 1960s. Professor Ray Lindsley taught hydrology in the civil engineering department at Stanford. Prior to becoming a university professor, Lindsley worked for the U.S. Weather Bureau, as it was known at the time, and was interested in flood forecasting. The tools available for flood forecasting at that time were primitive by today's standards. They used slide rules and historical flood records together with rain forecasts to estimate flood peaks. In many places, there was no historical flood records. Lindsley realized that if they could model the hydrologic cycle, they could create long-term streamflow records from long-term rainfall data. But developing a continuous computational model of the hydrologic cycle was the stumbling block. Norm Crawford was a graduate student at Stanford. For his PhD dissertation, he was instructed by Professor Lindsley, his graduate advisor, to create the computer code to allow for the calculation of runoff from rainfall using the entire hydrologic cycle. After numerous iterations, this led to the creation and publication of the Stanford Watershed Model version 4 in 1966. This was the first practical attempt to use digital computers to simulate all the components of the hydrologic cycle. This changed hydrologic modeling. Modeling all the components of the hydrologic cycle starts with the historical rainfall on the vegetation. Vegetation has interception storage, the amount of water stored on the vegetation before it gets down to the soil surface. Different types of vegetation have different amounts of storage. This is defined by the user. Once the water gets down onto the soil surface, then some of the water can become surface runoff, overland flow. Some can become interflow, shallow subsurface runoff, and some can become groundwater, deep subsurface runoff that can later become base flow. How much water goes where depends upon the soil characteristics. And finally, while all this is going on, some of the water in the soil and on the vegetation becomes evapotranspiration. Determining those different pathways and distributions and doing it in a way so that it can be used on any watershed anywhere was the key to the Stanford Watershed Model's success. The other key to its success was having the computational power to do all these calculations on an hourly time step for multiple years. Prior to the availability of large mainframe computers, engineers tried to do these calculations using just a slide rule or mechanical calculator. That just wasn't practical. But even with the use of computers, setting up the input data for the Stanford Watershed Model was not easy. All the input had to be key punched onto computer cards with one card per line of input. Input computer decks tended to get very large. I used to carry boxes of computer cards daily to the University of Washington Computer Center when I was running the Stanford Watershed Model in 1972 to model 2 local streams in the greater Seattle area. Setting up the rainfall data for the input to the Stanford Watershed Model was a major task. Typically, we got our data from the NOAA publication, Hourly Precipitation Data. We then had to hand copy the individual hourly values onto computer coding forms. And then once that was all completed, the data was key punched onto computer cards. It was a slow process that took days. Assembling the rainfall data was only the first part of the modeling process. USGS topo maps were used to determine watershed boundaries based on contour lines. Then the areas within the watershed boundaries were measured using a hand planimeter. We expected that usually would take a day or two. Within the watershed drainage area to be modeled, the soil characteristics had to be identified, defined, and the area measured for input to the model. Same with vegetation in impervious areas. The stream channel network also needed to be defined, measured, and input to the model. Finally, after all that work, the model could be run and results generated. If recorded streamflow data were available, that data could be compared with the simulated streamflow results. If the simulated streamflow did not match well with the recorded data, then the model input parameters could be adjusted to more accurately represent the hydrologic processes in the watershed modeled. If you want to know more about the Stanford watershed model and all of its trials and tribulations in its development, I highly recommend the article History of the Stanford Watershed Model by Norm Crawford and Steve Burgess. The continuous simulation approach would have been nothing more than an academic exercise if Norm Crawford had not started his hydrologic consulting firm, HydroComp, after he completed his graduate studies at Stanford. At HydroComp, he collected some of the smartest talent available out of Stanford University, including Delbert Franz, Brooke Traeger, Rob Johansson, and Tony Donigian. All of them would play a major, important role in the development of continuous simulation hydrologic modeling. The Stanford Watershed Model was public domain software written in the computer language ALGOL. Crawford decided to create a proprietary version of the software by rewriting it in PL1 and adding more features. This became HSP, HydroComp Simulation Program. HSP proved to be very successful, and HydroComp was awarded contracts to study hydrologic and flooding problems throughout the United States and elsewhere in the world. I joined HydroComp in 1973 and used HSP to model multiple watersheds in the United States, Canada, and the Dominican Republic in my 8 years with the firm. EPA became interested in continuous simulation hydrology and HSP. They weren't interested in flooding problems, but they were interested in the water quality of streams, lakes, and rivers. But they recognized that they couldn't accurately model water quality if the hydrology was not accurate. EPA didn't want to use a proprietary model like HSP, but they were willing to fund a public domain version of the software written in Fortran. For agricultural runoff management, they also added the nitrogen soil cycle and pesticide transport calculations to the model. EPA's version of HydroComp's continuous simulation software became the ARM model. EPA liked ARM and decided they needed a similar software package for urban areas. Urban areas generate their own set of pollutants that impact water quality. As a result, EPA again contracted with HydroComp to create the non-point source NPS model. This model focused on atmospheric pollutant deposition, accumulation, and runoff.